In today's video, we're going to take another look at the definitions of injectivity, surjectivity, and bijectivity. Highlighted in green are the explanations that I gave last time for what these definitions mean intuitively. You may recall them, you may not, but that's fine. The real point that I want to make here is that we didn't discuss bijectivity at length, which is today's goal. It's not because we define bijectivity in terms of injectivity and surjectivity. It's actually because bijectivity has a better interpretation than just what I've written here. This is just a definition of bijectivity. It's not the best way of understanding bijectivity. So with that being said, let's start by looking at this example here. I have a function that I've described by showing every single element in x as points and every single element of y as points as well. The arrows show you which elements of x get mapped to which elements of y. As I've drawn it right here, this is not an injection because this point over here is assigned to by two different points in x. You've got this one over here and this one over here. So this is not an injection, but you can really easily change it here. That does it. So all I've done here is made sure that every single point in y has a unique partner back in x. And notice already I'm starting to use this terminology of starting in a set y, the range, and going back to my set x. This is a little bit of foreshadowing for what we're going to do the rest of today. So an injection means we can basically find a copy of every point in x somewhere in y if we use f. Of course, the injectivity of a function does not actually depend on the set, it depends on the definition of the function. But one thing I would like to point out is that if I somehow removed one of these points in y, then this guy would have to get mapped to, well, it could get mapped to this guy or this guy, or it doesn't really matter. The point is that we would lose injectivity immediately. The reason being because no matter where it gets sent to, we're always going to have some guy in the range be assigned to by 2 points, and we don't want that if we want an injective function. Surjectivity I described a little intuitively last time using the examples of fruits and alphabets. So again, think of this as your set of letters, and these are your set of fruits. And we said that a function was surjective if for every letter of the alphabet, I could find some fruit that began with that letter. So here, if I define it like this, then this is clearly a surjection. But if I define my function literally any other way, like maybe like this, right? It's no longer a surjection because this guy is left over. So in other words, surjection means we can cover y, or big Y, with corresponding points, corresponding points in big X. Okay. Now, lastly, we have to think about what a bijection is. So a bijection has to be both an injection and a surjection. How could I possibly do this? Well, what does a surjection tell me? Well, it tells me that X has to basically cover all of Y. So there can't be too many points in y, or else it's not going to be possible to cover all of y. For example, this guy here is going to get left out. No matter how you rearrange these arrows, at least one thing in y is going to get left out. So there has to be at least as many elements in x as there are in y. On the other hand, if I have too few, then it's not possible to define an injection either. Notice here, again, that this guy has to get sent to one of these 3 points, and as soon as I do that, I no longer have an injection. And so we see intuitively a bijection represents a sort of perfect pairing between the two sets, x and y. So a bijection means we can pair elements in x with elements in y. And we have to do this perfectly, in the sense of no one gets left behind. So our goal in future weeks is to take advantage of these observations and intuitions in order to talk about infinite sets, where this sort of game with the dots and the arrows no longer works. The sizes of infinite sets are much harder to compare, but with some clever work and set theory, and using this idea of a bijection, we can actually come up with some very interesting and solid results. For the rest of this video, we have to focus on how functions interact with sets. So to start off, I'm going to try and motivate it by thinking about how a function acts, but only on a piece of the domain. We're going to let big X0 be a subset of X. So graphically, remember, this means that we have our set X0, and encapsulating all of it is the big X. Okay, so everything in X0 is in big X. And when we restrict the function f to a subset, we're going to denote it, like this. Okay, we will say f restrict to big X naught. Now, what does this mean? All this means is that I'm looking at what the function f does only on that subset big X0. So in other words, if I picked an x that was not in X0, then the restricted function f restrict x naught is no longer defined. We can also think about the image of this function. Now, again, the image is just a set of points in the range that appear as something that the function did to the domain. And when we restrict our function to a subset, it looks sort of like this, but we're going to come up with a better notation for it, and we will write this thing instead. Right? Now, this is technically not correct. We are writing here f of a subset big X naught, and this is technically not correct because big X naught is not an element of big X. So our function is technically not supposed to be defined on it, but we were going to do something called an abusive notation. And remember, I mentioned an abusive notation last time that high schools do. This time I'm doing my own abusive notation, but this is actually quite common, and it's used everywhere to denote the function applied to every single thing inside my subset. Okay? Let me just be clear in this case that the notation abuse is not meant to be confusing. It's actually meant to help readability and stay more in line with common conventions in mathematics. So in this case, the easy way of thinking about this new notation f of big X naught, or the restriction, or the image of the restriction, is that we apply f to every single point in big X naught and see what happens to it in the range. Here's my picture. So again, what I'm doing is I'm taking a subset of X, I'm applying f, or maybe f restricted to X naught, to every single point of my subset. Again, it doesn't matter whether I choose f or f restricted to X naught, as long as I stay inside big X naught, everything's still defined. The image of big X naught under f, or maybe f restricted to X naught, is going to be the set of points in Y that appear as images of the individual points in X naught. Right? So here we have the image of the restricted function. You may wonder if we've got a similar tactic going the other way. So in other words, pick a subset Y naught of Y, and I want to think about every single thing in X that got sent to Y naught. Okay? So all these points somehow ended up in here. Or more importantly, you may think, well, what happens if I just think about every single point that got sent to my single point here in Y? So I'll call this Y naught, and I'm thinking about every single point that may have been sent to Y naught. Okay? Of course, there could be more, there could be none, there could be one. And we're going to consider all these cases by creating a new definition called a preimage, which does exactly what we want. So a preimage is something that's defined in terms of a subset of the range Y. And it, in turn, is a subset of the domain, such that every single point inside this new subset are sent to something in Y naught. We will denote this as f inverse of Y naught, and if you're curious about the set notation, here it is. So we're looking at all the points little x in big X, such that f of x is some point in big Y0. So if big Y naught is a point, right, as I drew in this image up here, then we will write big f with a little -1 sign of that single point. Okay? So as an example, let this be a real function. This is the one that you're very familiar with, x squared. Think about the preimage of the two following sets, 0, 1, and the single point 2. You can pause the video and we'll come back to it. So if we look at this here, right, the preimage of everything in here, well, that's just all the points in the domain. So where's the domain? The domain is everywhere here, right? So that's the points in the domain that got sent to something in the interval 0, 1. And if we just draw vertical lines, you can see and actually check for yourself that this goes from -1 to 1. So we would say that the preimage of the interval 0, 1 is exactly the closed interval -1 to 1. Here's an example of looking at the preimage of a point. So here we have the point 2, but notice that 2 points get sent to 2. There's this one over here, which you can check is -√2, and there's this point over here, which is √2. Both of them get sent to 2, so we would say that the preimage of my single point, 2, is actually the set that contains plus or minus √2. Okay? So 2 simple examples of preimage, but here comes the big warning. You would like to think that our sort of notation here is similar to what you've seen in high school, the inverse function. Today we're considering, in particular, whether this thing that I've just written down here actually behaves as a proper inverse function. Unfortunately, the answer is often no, as the previous 2 examples have shown. There are several things that could go wrong. The first thing is that f inverse of y naught may not be defined on all of y. So again, what do I mean by this? The preimage of a single point y naught is just everything that got sent to that point from the domain. Okay? The issue is, though, what if the image of f was not all of y? In other words, what if f is not surjective? So in other words, here's all of x, and let's say all of x just gets sent to this little half portion over here. If I take a point here and I try to do something like an inverse function, this guy over here doesn't know where to get sent to because no one was initially sent to it. So that's not a huge problem, though. We could do a simple fix. We could just consider the image of f and ignore that fact that there's a y here and just replace it with the image of f. Right? There's absolutely no problem with that because my function will still be defined everywhere. It will still send a point in x to somewhere in my range if I just replace the range with the image. The advantage now, though, is that if my image is all that there is in my set, then it doesn't matter what I pick in this new range, there will always be at least something to go back to in my domain. But there's a second problem, and maybe you've seen it already in the previous example, is that the function, if I define it as an inverse function, may consist of more than one point, so it won't even be a function. And this happens in particular when f is not injective. You should try and justify this part to yourself. It's not an exercise, but it's just something that you should at least reconcile in your head. But there's no correction possible here. Basically, it means that once you have this non-injection, you're going to lose some data about your original domain. So again, what this would look like is something in the case where we have a point here, and more than one point got sent to y naught. In that case, you wonder, what would my inverse function send y naught to? Would it send it to this point over here or this point over here? And the answer is we cannot actually assign it a single point without losing some information about our original function f. And you're actually very familiar with this. The familiar example is, again, x squared, where the inverse, I put in quotation marks, is the square root of x. It's an inverse because the square root of x squared is exactly x, or actually rather the positive square root of a number squared is once again x. So as long as x is positive or non-negative, But the issue again is that if we're looking at this function, what it does is that it sends -2 and 2 to the same point. So when I ask you, what's the square root of 2? Or in other words, what is the inverse image of 2? Where should that go? The answer, of course, is that we have a convention, and that convention is that we just pick this guy over here. But in general, this is not even a good thing. So in general, this is undesirable, and especially when we're working in set theory, when we need to preserve information about the sets, well, this is actually completely useless. Okay? So in case you haven't got the memo yet, we're going to be using functions in order to probe the sets, because the sets themselves may have very complicated structures, or they may be even too big for us to consider. But if we think about how functions act on them, that can actually give us a better idea often of how the sets look like, at least in terms of size. So as points 1 and 2 suggest, there is one case where the inverse function, all right, does actually make sense. We require f to be a bijection. Okay? So here's an exercise for you that will appear in this week's homework. If you have a function that is a bijection, I just want you to show me that the inverse function is also a bijection. And the way we define our inverse function is basically just to undo whatever f did. Right? Undoability is an extremely important thing to have with your functions, and the more undoability you have, the better. And this is a common theme in all of math, by the way. Here's a fact that is basically going to summarize our entire discussion, but I'm not going to prove it because the proof is actually a little tricky. If I have a bijection f, then it has a well-defined inverse on all of its range. Conversely, so that means going the other way around, if I know my function has a well-defined inverse on its range, then I know that my function has to be a bijection. This point over here is probably the most important part of today's lecture, because what it does is that it allows us to basically come up with a sort of criterion for whether a function is a bijection or not. We don't even need to care about whether or not it's injective or surjective. Those things will come naturally. And over here, I've outlined the logic of the previous statement using some of the logical symbols that we've become acquainted with. And basically, if you read this and understood what we did last time, you should come to the conclusion that f is a bijection if and only if f has a well-defined inverse. And I've put for you here, in case you don't remember from high school math, a well-defined inverse just has to have these properties. Now you may wonder why I've put y here instead of x. Well, that's just to remind you that the little y is an element of big Y and little x is an element of big X, right? So we'll keep these two conditions in mind as we go through two examples. Okay? So our first example is the function that takes a natural number and sends it to its negative. You probably already have an idea that we can undo this. And how do we undo this? Well, we just have to multiply by -1 again. But in math, we have to prove things. We have to prove that this is actually a well-defined function. So we will show that it is a well-defined inverse by proving, as we had in our two criteria up here, f inverse of f of x is x, and f of f inverse of y is y. So let's do this. Well, what does f of x tell us? X again is just some number. Well, f of x is just going to be -x. And what does my inverse function, the function that multiplies by -1, do? Well, it's just going to multiply this thing by -1 again, and I'm going to get x. So this is good. This is exactly what we wanted to show. Again, these equal signs here are really, they really should be equal signs with a question mark because we don't know whether or not they're true. We would like them to be true because that's what we're trying to show, but beforehand we don't know they're true, so we can't pretend they are equal signs. So really what I'm going to do for this next one is do it properly. I'm going to erase this here, and then we're just going to note that f inverse of y, well, I just multiplied by -1, I get -y. And then what is f of -y? Well, remember, negative y has to be a negative number, so we can multiply by -1 again, and it will send it to its negative, which is negative of negative y, or y, right? And this is exactly what we needed to show. So we're good here as well. So therefore, our function is actually a bijection. To do one last example a little faster, we'll take a familiar function, x cubed, and you know already that it has a really good inverse, which is the cube root of y again. Why am I using y? I should put a negative here. Why am I using y? I'm using y to remind you that this is an element of range. And I leave it to you to check the following, that these two conditions are satisfied. The work here is shown for you in case you can't get it on your own, but these are really just simple properties of exponents, and they should not be any different from what you do in regular high school arithmetic. All right. Sorry, I just noticed something here. I should have put a y here to be consistent, but you know what? It'll be fine. Okay. So one thing that we're going to do in the exercises is we're going to find a criteria using only the words preimage to describe whether a function is injective, surjective, or bijective. We've already sort of discussed what it means for a function to be bijective. It just means that the preimage has to contain exactly 1 point, right? And it has to be defined, of course, everywhere on the range. So in our example, f is a bijection, or is a bijection if every point has a preimage satisfying. Well, here what I really want to say is that the preimage that consists of exactly 1 point, no more, no less. So in the homework, you will be asked to find equivalent criteria in terms of preimage for injectivity and surjectivity. So that's going to end it for this week's asynchronous lectures. And hopefully next week we are going to be ready to tackle on the more serious topics of the pigeonhole principle